I'm interested in vectors and mechanics question here. First of all, let's deal with the vectors part. We've given a regular hexagon and P and Q defined as shown. And then we've got 5 different forces being applied to a particle, and we're asked to work out the resultant force. So I think first up, I'm going to write down each of the vectors. OP is simply going to be P. That one's not too bad. OQ. Okay, that one's quite nice as well. That's just going to be Q. But then if I have OR, then I'm actually going from here to here. So I need to figure out how I can do that. Um, and one thing to realize early in this question is that we're told it's a regular hexagon, which means we can split it into not three, 6 equilateral triangles, and we can use the properties of that. For example, TQ is going to be twice what OP is. Okay, so I want OR, and that means what I could do is I could go from O to Q, and then I could go back to P, and I could go from T to R. That would get me there. So OR is going to equal Q plus Q minus 2R. So 2Q minus 2R. Sorry, 2P. Did I say R there? So I'm going Q minus P plus Q. Give me 2Q minus 2P. Okay, so I've sorted these. Right, OS. Let me do this one in green actually. Okay, now I want to go straight up. Okay, what can I do here? So I can actually go from OR and then just minus another P, actually. It's not as bad as I thought. I can just use that. So it would be 2Q as normal, but then I'm going to be minusing 3P. There's other ways to work it out. This is just one option. And finally, OT. Okay, so I want to get to here. Right, actually that's not too bad because I can get from O to Q and then just minus 2P. So it's actually going to be Q minus 2P. Okay, and I'm nearly there. So the resultant, which I'm going to call R, I actually called it F when I was doing it myself, but R does make a bit more sense and the solutions use that. So R is going to be the sum of all of these. So it's going to be OP, which is P. Let's do this carefully, plus 2 times OQ, so that's 2Q, plus 3 times OR, so that's 3 times 2Q minus 2P, plus 4 times OS, plus 5 times OT. Okay, there we go. We can expand the brackets. I'm running a bit out of space, so I'm going to come down here. So R is going to be P plus 2Q plus 6Q, just expanding this bracket here, minus 6P plus 8Q minus 12P plus 5Q minus 10P. Okay, we're nearly there. Let's get this resultant force in terms of P and Q. Let's add the like terms. So I've got P minus 6P, so that's minus 5P, minus 12P, that's minus 17P, minus another 10P, minus 27P. And then 2Q plus 6Q, that's 8, 16, 21. Good. We're then told that the magnitude of the acceleration is 13 and the mass is 3, and we're asked to work out P. So we can use F equals ma to link them all together. And in our case, it's going to be, and this, by the way, I'm writing them as scalar quantities because I have the magnitude of the acceleration. So the magnitude of the force is going to equal 3 times 13. let's work out this magnitude then. Okay, now be really careful to find the magnitude of a vector when it's written as, I don't know, 5, like 4i plus 3j. You can just use Pythagoras' theorem because we're going along and up. But here, q and p are not going, like q particularly is not going up. So we've got to think about it a little bit more carefully. So we've got q as 21q. I'm just going to draw it on, going in roughly the direction that it is on the diagram. And so it's going to be, actually, I'm going to draw it as a triangle, not as vectors. So 21q, where q is the magnitude, like q is equal to the magnitude of q, and p is equal to the magnitude of p. And of course, this is the one we're actually trying to find. And then it's minus 27p. So I'm going to be going this way. And we can see from the diagram that q is longer than p. So even though I'm going back by minus 27p, I don't think I'm going to get back all the way to here. And therefore, do you know what? I will just put on the vectors. So I'm going here and then I'm going here. So my overall vector actually is from here to here. That's my minus 27p plus 21q. But back to the magnitudes, I've got this is the size of this is going to be 27p. And I want to work out what that is because that will be the magnitude. Well, is there anything else we know? Let's just take a look at the regular hexagon again. So actually, I'm interested in finding this angle here because that is the same. I'm going along some amount of q and then back this way. So if I can find that, I can put that in my triangle. And remember, because this is a regular hexagon, then the angles are all 120 inside it. Number of sides minus 2, that's 4, times 360 divided by 6, 120, which means that this angle is 30, and therefore this angle is 30. And then we actually have alternate angles, because here's my z, so that angle, that missing angle there, the question mark, is also 30 degrees. We have an angle in this triangle, 30 degrees. And I can now use the cosine rule because I've got these two sides and then the opposite angle. So I'm calling it question mark, but it's actually r, remember? R is the magnitude. Right, before I just carry on, let's just backtrack. Just want to check that you're happy with everything. So I'm hoping you're okay with the forces. I worked out all of the vectors quite carefully, quite a nice little question here. And we got them all, we then added them all up, combined the terms to give this as the resultant. We're then told that the magnitude of the acceleration is 13. So I've used F equals ma to get a relationship for the magnitude of the force, and that's going to equal 39. Let's leave it as 3 times 13 for the moment. And now I know what r is, so I want to work out the magnitude of r in terms of p and q. They're not perpendicular vectors, so I need to think about it more carefully. I've drawn a diagram to show that I'm going along 21q and then back 27p. I'm going to create a triangle force diagram essentially, and r is this blue one here. That is the vector, but actually remember I want the magnitude. So I've got a triangle, forget the vectors now. I've got a triangle where I know two sides and the opposite angle, so I'm going to use the cosine rule. R squared is going to be 21q squared plus 27p squared, because it's, remember, it's c squared equals a squared plus b squared minus 2ab cos c. That's the one I always use because it links to Pythagoras' theorem nicely. And then I'm minusing 2 times 21q times 27p times cos 30. Now cos 30, that's an exact value to know. It's actually root 3 over 2. So the 2 and the 2 cancel there. And then r squared is actually going to be 3 squared times 13 squared. And you know what? I'm just going to leave it like that for the moment. So I've got the magnitude, and I've got got it in terms of q and p now. So 3 squared times 13 squared is equal to all of this. Just going to rewrite this to make it a little bit neater. So 3 squared times 13 squared is equal to, what I can actually do is factorize the 3 out. So I'm going to have 3, so 21 is 3 times 7. So 3 squared times 7 squared times q squared plus 3 squared times 9 squared times p squared. Factorize the 3 squared out of this one. And then I'm going to be minusing 3 squared times 7 times 9, and then pq root 3. Because 27 again is 3 times 7, 27 is 3 times 9, so I've just factored it all out, and now I can just divide through by it. Okay, that's potentially going to be useful. Now, it's still not enough as things stand, because I've just got an equation with two unknowns in, so we've got to think, is there any other way of linking p and q together? And the answer is yes, because remember, this is 120 degrees, and this is a regular hexagon. These two sides are the same. I have an isosceles triangle. I can draw a line going like that. And if I draw the triangle out on this bottom one here, then I have P, I have a right angle, I have 60 degrees because I'm splitting that 120 into 2, and this is actually going to be Q over 2 because I'm splitting it into a half. So I can write down that sine 60 is the opposite, Q over 2, over the hypotenuse P. That means P sine 60, and P sine 60 is root 3 over 2, because sine 30 is a half. So P times root 3 over 2 is equal to Q over 2, meaning, there we go, Q is actually root 3P. Got the relationship between the magnitudes. So I can now sub that in to this equation here. Okay, we're nearly there. Remember, we're trying to work out what P is. So subbing in for Q is absolutely perfect. Okay, let's leave it as 13 squared for the moment. That's going to equal 7 squared times Q squared, which is going to be 3P squared. So 7 squared times 3P squared plus 9 squared times P squared minus 7 times 9 times, and root 3p, remember, is q, so I'm going to get another, wait, sorry, I want to replace q by root 3p, apologies, so that should be 3p squared. Okay, I can't really avoid figuring this out on the right now, so I'm going to have 49 times 3, that's 147 p squared, plus 81 p squared minus 63 times 3, that's going to give 189. I'll just leave it as 13 squared for the moment. Okay, 147 plus 81 gives 228. Then 228 minus 189. Probably best to just add on, actually. Add on 11 to get to 200. Add on 28. It's going to be 39. So 13 squared is equal to 39p squared. And it actually did help out to leave it as 13 squared because 13 goes into 39. I can just divide through by 13. 13 is equal to 3p squared, which means p squared is equal to 13 over 3, and hence p. Remember, p, we're interested in the magnitude here, so it's not plus or minus. Let's actually bring back in this. The magnitude of the vector is going to be the square root of 13 over the square root of 3. Whoops, what am I doing? Square root of 13 over 3. But I was getting ahead of myself because we could write it like this and then rationalize the denominator times top and bottom by root 3, which gives root 39 over 3. But both of these are absolutely fine answers. You'd probably argue that this one's slightly neater, so I'll put a box around that. Oh, good question on vectors. Well done.